study. All you're doing tomorrow is taking your test. Pen, pencil, ruler, and calculator. That is all you will need for your class tomorrow. That's it. Okay? All right, let's go through the study guide. Hopefully you knew most of these answers. That was not a surprise. Thank you. All right, so basically we're looking for patterns and trends starting on page 29. So the variable t is only a scalar, which stands for time. The units it's measured in are called seconds, which we abbreviate with a lowercase s. The letter d, if it's a scalar, refers to distance. If it's a vector, refers to displacement, always measured in meters, which we abbreviate with a lowercase m. V, if it's a scalar, refers to speed. If it's the vector, it refers to velocity. It is measured in meters per second, which we abbreviate as m over s. A is only a vector. It stands for acceleration, measured in meters per second or meter per second squared, abbreviated m over s squared. Position is number 1 in the definition. 2 is distance. 3 is displacement. 4 is speed. 5 is velocity. 6 is acceleration. And 7 is time. Those are the definitions of those physics terms. Now, there are 6 equations that you should know for tomorrow's test. Do you have to memorize all of them? No, you only need to memorize 1 of them. The other 5 are already on your reference table. The first one that's on your reference table that works with accelerated motion is V bar is d over t. This shows it being rearranged for d, which is V bar t. That's the same thing as t is d over V bar. But you're going to start with this when you do a problem solving yesterday or tomorrow on your test. Then number 2 is the one you have to have memorized. The other equation for V bar. That is VI plus VF over 2. You should have written that on your reference table that you have. So that way you have it to help you prepare and do problems in the future. Number 3, from your reference table, A is change in V over T, and then you should have expanded it like I did in the video. So it looks like VF minus VI over T. That's how it should be written on your reference table, all of that. So you get the change in velocity by doing the final value minus the initial value. So the change in velocity is acceleration times time, or the time is the change in velocity over the acceleration. Number 4, we have VF is VI plus AT. You should be able to move it around for all the other variables in that equation. We have VF squared is VI squared plus 2AD. Again, you have to be able to move it around for all the variables in that equation. And number 6, D is VIT plus half AT squared. Same thing, you got to be able to move it around for all the variables in that equation. All right, let's go to page 30. Let's start with just the position time graph column, okay? We're going to go down the column for position time graphs. The dependent variable is position. The independent variable is time. The y-intercept refers to the initial position of the object. When you are at rest, you're going to see a horizontal line on your position time graph. When you're moving with a constant velocity, you're going to see a diagonal line. When you are accelerating, you're going to see a parabola. If you're moving fast, the graph will be steep. If you are moving slow, the graph will be shallow. If you are moving in the positive direction, your graph will go up. If you are moving in the negative direction, your graph will go down. If you are looking at the slope of this graph, you're finding some type of velocity. The area will never be, you're never going to find an area on a position time graph. That means it's meaningless. The displacement is looked at or found by looking at the rise or the drop of your graph, the change in the y coordinates. And your average velocity is calculated by looking at the slope of a secant line. The instantaneous velocity is found by looking at the slope of a tangent line drawn at the time point. And your acceleration cannot be calculated directly from a position time graph in the Regents course. All right, let's go to the velocity graph column. The dependent variable is velocity. The independent variable is time. The y-intercept represents the object's initial velocity, the VI. When you're at rest, you're going to see a horizontal line on this graph at a value of 0. Must be on the x-axis or cross the x-axis at that time. When you're moving with a constant velocity, you're looking at a horizontal line that's either up in quadrant 1 or down in quadrant 4, either above or below the x-axis. When you're accelerating, you're always going to see a diagonal line. If you're moving fast, your line is far from the x-axis. If you're moving slow, your graph is close to the x-axis. If you're moving in the positive direction, your graph needs to be above the x-axis in quadrant 1. If you're moving in the negative direction, your graph should be below the x-axis down in quadrant 4. The slope represents the acceleration of the object. If you're calculating an area, you're looking at the displacement. You can find the displacement on the graph by looking at the area between the graph and the horizontal axis. Another way to do it using the kinematics equations to start with V bar is d over t, so d is V bar t. You could take the average velocity, which we'll talk about how to find on your graph, and multiply it by the time interval, and that will also give you the displacement. To get the average velocity, you have one of two ways. You can either calculate it using the equation that you had to add to your reference table. V bar is VI plus VF over 2, right? You average two values. Or you can go to the middle time and just go up and over and read the graph at that middle time, and that will give you the average value. So for example, if I wanted the average velocity between 0 and 2 seconds, you would read the graph at 1 second. That's the middle time. Instantaneous velocities are just found by reading the y-coordinate off the graph at that time, and the acceleration is found by calculating slope. All right, let's go to page 31. I'm going to go column by column, okay? So let's start with the velocity column. If you're not moving, your velocity is 0. If you have a constant velocity to the right, the word right tells you the velocity is positive. If you're going to the left, that means your velocity is negative. Doesn't matter whether it's constant or not. Right means positive velocity. Left means negative velocity. If you're speeding up to the right, right, positive velocity. Next one, left, that's got to be a negative velocity. The next one says right, so guess what? Positive velocity. The last one says left, so that's negative velocity. All we look at is the direction to tell us the sign of the velocity. All right, acceleration. There isn't any acceleration if you're not moving or if you're moving with a constant velocity. So all three of those are no acceleration. Now, when you speed up, your acceleration is in the same direction as the velocity. So since this velocity is positive, the acceleration is also positive. Speeding up in the next one, velocity was negative, so acceleration has to be negative. They have to be the same directions when you speed up. When you slow down, they are opposite. So the next one has to be a negative acceleration because it had a positive velocity. The last one's a positive acceleration because there was a negative velocity. You seeing the patterns? You just got to know those patterns. Okay, let's draw the ticker tapes. The ticker tape for no motion is just one single dot. That's a blob. The next has an arrow going to the right because you're traveling to the right, and the dots need to be equidistant because you're going to read it going to the right. This one, you're going left, so we put an arrow over it pointing left. Dots, again, are equidistant. We would be reading it this way. Next one, speeding up to the right, arrow going to the right. Speeding up means the dots get further and further apart as we go from left to right. The next one, speeding up left, so we need an arrow to the left. Here we should see the dots getting further and further apart as I read it from right to left. Slowing down to the right, arrow to the right. Dots get closer and closer and closer together as we read it this way. Slowing down left, dots get closer and closer together, but we need to read it from right to left. Any questions on those so far? All right, let's talk about what the position time graphs are going to look like. When you're not moving, it's any horizontal line. Doesn't matter where it is. Constant velocity to the right needs to be a diagonal line, positive slope. Doesn't matter where. Any diagonal line with a positive slope. Constant velocity to the left, any diagonal line with a negative slope. Speeding up to the right has to be a parabola that goes up and gets steeper. Doesn't matter where it is, but it needs to go up and get steeper. The next one, speeding up left, has to go down and get steeper. Again, doesn't matter where the parabola is. Slowing down to the right, a parabola that goes up but levels off. Doesn't matter where it is. Slowing down to the left, it's a parabola that goes down and levels off. Again, doesn't matter where it starts. The velocity ones, it does matter where it starts. Hold my paper so I can just show that column. Thank you. Thank you. Thank you. Thank you. All right. No motion. Horizontal line on the x-axis. Constant velocity to the right. Horizontal line up in quadrant 1. Constant velocity left. Horizontal line down below the x-axis. Speeding up to the right. Diagonal line, positive slope. It has to be above the x-axis. Speeding up left, diagonal line, negative slope. It's got to be down in the 4th quadrant. Slowing down to the right, diagonal line up in the 1st quadrant with a negative slope. Last is diagonal line, positive slope down in the 4th quadrant. Any questions on those 3 pages? All right, let's then talk about the acceleration pages. Concept stuff. Number 1, acceleration is the rate of change of velocity. Number 2, it's a vector, so it has to have both the magnitude and the direction. Number 3, average acceleration is change in velocity over time, or VF minus VI over T. Units for acceleration are meter per second or meter per second squared. 3 ways to accelerate are speeding up, slowing down, or changing direction. If your initial velocity and acceleration are in the same direction, you are speeding up. If they're in opposite directions, you're slowing down. Define these types of acceleration. A constant acceleration refers to a constant rate of change in velocity. An instantaneous acceleration is a change in velocity at one moment in time. An average acceleration is how your velocity changes over some length of time. In our course, we only deal with constant accelerations, so all 3 of these would be the exact same thing. You're not going to have any difference in those in this class this year. Number 9, how does initial velocity and final velocity differ? Your initial velocity is your velocity before acceleration. Final velocity is after acceleration. Another way to define that, your initial velocity is the velocity at the starting time. VF is your velocity at the ending time. Number 10, please change that. There are 6 constant acceleration equations that you should know. These are in no particular order. VF is VI plus AT. D is VIT plus half AT squared. VF squared is VI squared plus 2AD. A is change in V over T. V bar is D over T. And V bar is VI plus VF over 2. Okay, the rest of this was all multiple choice. So I just need to give you the final answers to those multiple choice. And once we get all those answers, I'll take questions on the multiple choice to help you out with anything you don't know. All right, so this is now page 34. Number 1 is D. Number 2 is D. Number 3 is A. 4 is B. 5 is D. 6 is A. 7 is C. 8 is D. 9 is A. 10 is B. 11 is D. 12 is D. 13 is C. And 14 is C. 15 is C. 16 is A. 17 is C. 18 is B. 19 is D. 20 is D. 21 is B. 22 is A. 23 is A. 24 is B. 25 is A. 26 is A. 27 is C. 28 is B. 29 is A. 30 is A. 31 is A. 32 is C. 33 is C. 34 is A. 35 is B. 36 is B. And on the last page of these types of multiple choice, 37 is A. 38 is C. 39 is D. And 40 is A. All right, the last two pages, which were mostly guess method questions. Number 1 is 3. Number 2 is 4. Number 3 is 2. 4 is 3. 5 is 2. And on the very back of your packet, 6 is 3. 7 is 4. 8 is 2. And 9 is 4. All right. Take these off the screen. I think we just now need to focus on pages 34 to 42. All right, so here's what I'd like to do. When you ask a question, you need to tell me two things. What page number are we looking at first? And then what's the question number? Page number, question number. Anyone have a question? Yes, Brady.
Page number 39, question 36.
Page what?
Page number 39.
39. I thought you said 49. I'm like, there's no 49. 39, question 36.
Yeah.
Okay. So let's take a look at this graph. I'm asking you for the average velocity between C and D. C is here, D is here. There's two ways to get it from a velocity time graph. You can either use the equation that you're going to memorize, VI plus VF over 2, or you can read the velocity at the middle time point. I'm going to do it both ways. So if I do it this way, the VI would be at point C, which I see is 10 meters per second. The VF would be at point D, which is 25 meters per second. So that gives me 17.5 meters per second. Okay, if I do it at the middle time, C starts at 6, D is at 10. What's the middle value? 8. So I would go up and over, and that number right there is the average velocity. So that's 17.5, which is choice B. Morgan.
On the back.
Yep.
Page 42.
Yep.
Number 8.
Number 8. Okay, these are guess method questions. Here we don't say left and right or positive, negative, so you have to assign signs to every value. So when I circle, this is one given. We have another given here. Whoops. And that says to the north, so I got to add that in. And then I have 4.0 seconds. I'm looking for displacement. Okay, so when I start with my givens, I'm first going to assign the direction north to be positive. North is like up on our XY axis, positive Y. So that means our VI is positive 10 meters per second. This is an acceleration, meter per second squared. It says north, so that's a positive value of 3.0 meters per second squared. That last given is a time, 4.0 seconds. What is unknown is the displacement. So we're going to go to page 6 of our reference table. You don't have to have these equations memorized. You just have to have those memorized. So the one that works with the variables given, VI, AT, and D, is this one here. D is VIT plus half AT squared. All right, so now I'm going to plug in substitution with units. So positive 10 meters per second times 4.0 seconds plus 1/2 of positive 3.0 meter per second squared times 4.0 seconds squared. So now you're going to go to your calculator. You're going to plug that in. 10 times 4 is 40, positive 40. 4 squared is 16. Half of that is 8. 8 times 3 is 24. So that gives me an answer of positive 64 meters, which is the same thing as 64 meters positive is north. So 64 meters north, choice 2. Anything else? Lisa? Question 21. All right. So we're giving you this velocity time graph, and I want to know at what value of time t are we back at the starting point? When you get back to your starting point, that means your displacement is 0 meters. You haven't changed position over the time interval. And the way you get a displacement on one of these graphs is by looking at your area between the line and the horizontal axis. Now, the horizontal axis is here. That's the horizontal axis because that's where our y value is 0. So that means if I were to start shading in areas, notice that everything between 0 and 5 seconds is going to give me an area that is positive because I'm above the time axis. The area between 0 and 5 is only positive. I need a value for an area of 0. The only way I can get a 0 area, the 0 value of anything when I have something that's positive, is add something negative to it. Where would I get negative area? After 5 seconds, because now I'm below the velocity axis. So when I look at this, I see of the 4 choices, the only one that goes beyond 5 seconds is 8.5 seconds. So that has to be the correct answer. If I look at the area at 8.5 seconds, there's my line at 8.5 seconds. I go down to the graph and I shade in. That area there is negative. And it must be that that positive area and this negative area are equal in size. I don't have to calculate it, but that's the only one that would make sense. Another way to think about this is that it tells you that you start off at rest, which we can see on the graph, 0 meters per second, and we start going north, which means everything here is north and everything here is south, right? That's what a negative velocity would have to mean, south. So here's what I did. I started off at rest at some point, and I started moving north, speeding up. Then I was still going north, but slowing down. At 5 seconds, I am as far north as I possibly can be. The only way I'm going to get back to my starting point over there is if I then travel backwards, which is not left, south, which means I got to go now this way. Now I turned around. At 5 seconds, I turn around. I was going north. Now I'm going to go south. Going south, speeding up. I travel at a constant speed going south, and then boom, there I am back at my starting point. That's the way we'd have to think of that. Brayden?
If the y-axis had position, then would it be 5 seconds? Like if the y-axis was velocity,
Right.
Position,
Yep.
it would be 5.
Yep. And 11.
Yeah.
And 12. And 13. And 14.
Yeah.
But it's not a position time.
Yeah. I'm just,
And that explains question 22. If you said east and west, you did not read the question. You see it says north up here? So the only possible answers are north and south. At 4 seconds, I go up and I see that velocity is in the north quadrant. So therefore, at 4 seconds, I was going north. That's how that one gets done, in case any of you were wondering. It's reading the graph. Anything else you want to ask on those multiple choice questions? Anywhere pages 34 on. Yes, Caroline.
Can you do page 37 and page 27?
Okay, notice that these are all speed time graphs. You could calculate the distances, but that takes a lot of time and you don't need to do that. Remember that distance on a graph of speed time is the area. So what I want to do is just shade in these areas. If I want the greatest distance, I want the biggest area, the biggest shape. So let's shade them in. There's a triangle, rectangle, trapezoid, trapezoid. Which of those is the biggest? C. You see that's the biggest shape? Therefore, that's the greatest distance. So by understanding some of these patterns, you can visualize the answers to these questions instead of spending the time calculating. If you wanted to calculate them, that's fine, but it's going to take a lot more time. And I know a lot of you are like pushing up against the end of the period to get things done. So I want to make sure that, if you understand how to do it by just visual, a lot of us are visual people. You see something and it makes more sense versus having to calculate it out. If you can visually do it, do it. Sorry, I'm just boiling right now. Lovely stage of my life. If you're freezing, I'm sorry. I'd like to give you some of my body heat. Just throw it out in the room. What else can I do to help you? Yes, Havisa?
For page 42, number 9, how would you know if it's north or south?
Okay, so here's what I'm going to first clarify. You're never going to see the word decelerates in any question I give you on a test. Never. I think I may have mentioned that in one of the videos. Decelerates was eliminated from our Regents physics curriculum back in 1996 because it's a confusing term. Instead, we always will say slow down. Okay? So this object is initially going at 20 meters per second to the south and slowing down. What's the direction of your velocity after you slow down? So I want you to think about it. You're driving on the Northway going south. From here going towards Crossgates Mall. You step on your brake to slow down. Which way is your car headed after you step on the brake? Still going south. So you know it's got to be a south answer. 2 or 4. Now, you're slowing down. You started off at 20 meters per second south. Could it ever be 26 meters per second south if you're slowing down? No, because 26 would have been speeding up. So you didn't even have to use the guess method to solve this one, but let me show you how you would if you did, okay? So there's a given. Here's a given. Here's a given. You're looking for this. So to do this through calculation, we are told your initial velocity, usually south, is a negative direction on our XY axis. So that would be negative 20 meters per second. Now, when you slow down, you need to know that your acceleration is always opposite direction, which means your acceleration is not south, it is north, which is the positive direction. Now, Your displacement is in the direction you traveled. You're traveling south. So which way did you displace yourself? You end up south of where you started. So we end up with a negative 25 meter displacement. What is unknown is our final velocity. The only equation we have on our reference table with a VI, an A, a D, and a VF is this one here. VF squared is VI squared plus 2AD. So that's the equation I'm going to use. Now it's not solved for VF. It's solved for VF squared. So you have to solve it for VF next if this were show work. This is the algebraic manipulation. Now, anytime you have a square root and you're looking for the vector, you have to decide whether the answer is positive or negative. And I think we already talked about why it's negative. If you think about it, you're traveling south and slowing down. After you step on the brake, your car is still pointing south. So we need a negative answer. Now I can go ahead and plug in, doing my substitution with units. So negative of negative 20 meters per second squared plus 2 times positive 6.0 meter per second squared times negative 25 meters. You work this all out, and you're going to get the answer of negative 10 meters per second. And that negative sign, as we've already stated, means south. By the way, you would never say negative 10 meters per second south. The negative means opposite of a stated direction. So what does negative 10 meters per second south equal? And that's the same as 10 meters per second north, which is not the correct answer. So if you wrote this on a test, the negative and the word south, it's going to be marked wrong. Okay? It's one or the other. So you would just say this, but then you have to know, because it's multiple choice, what does that negative mean? It meant south, so 4. Okay? Anything else you want to ask? We still have 7 minutes left to ask questions. Anything at all that you want to ask about?
Can we go over question on page 40, question 38?
Yep. Okay, so this question's asking you how far something traveled. That means the distance. How far did it travel? Now, the kind of graph you have is speed time. The way you get a distance is either by looking at the area or by using average speed as distance over time. So distance is average speed times time, one or the other. I'm going to do it both ways. Okay, so you can see it both ways. I'm going from 0 to 60 seconds. Here's 0, here's 60. This is car A. There's the line. So if I look at the area, I'm looking at that shape there, which is a, what shape? Triangle. The base of that triangle is 60 seconds. The height of that triangle is 60 meters per second. Half of 60 is 30. 30 times 60 is 1,800. So that's one way to get choice C. The other way is to do it with your kinematics equation. But the first thing I have to figure out is the average speed. 0 to 60 seconds. What's the middle time? 30. So I'm going to go up 30 and over, and that is my average speed, 30 meters per second. That's happening for 60 seconds. What's 30 times 60? 1,800 meters. The other way to get that average speed would be do VI plus VF over 2. The initial speed would be the speed at time 0, which is 0 meters per second. The final speed would be the speed at 60 seconds. 60 up and over, I see 60 meters per second. What's the average of 0 and 60? 30. Isn't that what I plugged in right there? So there's a lot of different ways to get these answers. Make sense, Braden?
Yeah.
Okay. For multiple choice, you can pick which way you want to do it. Because I'm only going to look at your final answer. Nothing? Nothing else? You sure? You certainly have enough to study to help you practice for tomorrow's test. Remember, we talked about after the last test, the way you do better on my test is by practicing. Studying is practicing. You're trying to build, think of your brain as a muscle. I know it's an organ, but it's really a muscle. Making those neurons connect so you remember and understand things involves practicing. Yeah. 37, let's look at 28. Okay, so these I am actually going to calculate average velocities or read them. I'm going to go to the middle time for these two graphs. So let's start with the average velocity for object A. Object A goes from 0 to 3, which means the middle time is 1.5. Up and over. That value is 17.5 meters per second. It's the average of 0. Actually, is it 17.5? No, it's the average of 0 and 30. What's the average of 0 and 30? 15. So A's average is 15 meters per second. What is it for D? So D starts at 10, ends at 30. What's the average of 10 and 30? 20. So now, I know these comparison questions can be tricky. It's really now a reading question. To help you out with this, ignore the first phrase. Start after the comma. The average velocity of D is, this is bigger than that. So it's got to be greater. Just look at the last phrase to help you figure out whether, otherwise I know sometimes we switch. You're telling me what A is compared to D instead of D compared to A. You actually had the physics right, but your reading comprehension is a little up. So I'm trying to give you some skills to help you with that for better test taking. Anything else? You're all looking at me like you're either completely overwhelmed or you got this. I don't know which it is. Hello? Yes. Okay, Bridget, how are you? You got it. You're welcome. Okay, bye-bye. You sure nothing? Okay. Then this is what I'm going to ask you to do. You're going to put away your Unit 3 packet. You're just going to keep out your reference table and your notebook and something to write with, because next period we are going to start Unit 4A. And what I'd like to do, the time I have left, is just start getting ready for that. So I'm going to ask Anya and Aiden to take yesterday's quiz. Just follow the directions at the top. You can use your reference table, your calculator, and yesterday's homework. Use your reference table, calculator, and yesterday's homework in your packet. And the rest of you, go ahead, take your break. Just, yeah, you know, your principal class, right? You're welcome.
Okay, on. Expensive.
All right. So, folks, as I mentioned, you need your notebook, something to write with. That Unit 4 packet we're actually not going to get to today, so you can put that away. I'm just handing it out for now. Just notebook, something to write with, and your reference table, because there is a couple of things we're going to check off on the reference table today that deal with Unit 4 on dropped objects. Thank you, Anne. All right. Tomorrow, as I said, just pen, pencil, ruler, and calculator for your test. Okay, so you'll get here, you'll start right away. You have till the end of the period, and that's it. Okay, so Unit 4 is a continuation of our study of kinematics. And specifically, what we're going to do is we're continuing our discussion of acceleration. We're going to talk about a very specific type of accelerated motion now. In Unit 3, everything was accelerating in a line parallel to the floor, either this way or this way or that way, but it was always moving parallel to the ground. Objects can accelerate and have a type of acceleration known as free fall, which involves acceleration up or down perpendicular to the ground. And that's what we're going to talk about in this unit. So it's a lot of overlap with what we learned in Unit 3, but now we're going to talk about a specific case that's up or down, not north-south. When I throw something up in the air, it's not moving north. North is towards Canada, okay? That way. So we're going to start off by talking about objects that fall or dropped objects, things that fall. A lot of you have probably been to amusement parks and been on these free fall rides before. This is not my cup of tea. I would be vomiting on these things. I think these are photographs from an amusement park in Texas, one of the Six Flags amusement parks. I think it's Great Adventure is the one in Texas. But what they do is they bring you up. You can see there's 4 people on this. They bring you up to the top. You're strapped in, of course. And then it just releases you. The mechanism just releases until you get to about here where the brakes start to be applied. So you're just being dropped for a good distance, which is scary. So not my thing. If it's good for you, more power to you. I know people that love to go to amusement parks. That's not my thing. But anyway, what I will ask you to do, the quiz on this will be Friday. There's only 2 sections in this unit, so we'll have one quiz Friday, one quiz Monday, test Wednesday. This will be your first test of the second quarter. This test grade does not go in first quarter because you need time to correct it before I put in your quarter grade. So just keep in mind. These are the things you'll be quizzed on. I'll ask you to define what we mean by acceleration due to gravity. You'll have to explain what the term free fall is. We'll then have to use our graphs and equations to describe falling objects. We have to correctly solve problems with our 7 steps and use our kinematics equations as well. So it's pretty much everything you need to be able to do for tomorrow's test, but for this type of motion, up or down. In this case, specifically down to the ground. Basically, we're talking about this. See my pencil? That. You have to describe that with all of the tools we already have. So let's describe what free fall is. Free fall is when objects fall under the sole influence of gravity. That word sole means the only thing influencing its fall is gravity. Specifically, it means that there won't be any air resistance to consider. No air resistance to consider. Can we truly experience free fall here on Earth then? No. We can't because we have air. Okay, it means that any experiment we do in our class, We can't do experiments with free fall in our class. We have a big problem. If I evacuated all the air in this room, we have a big problem. You won't be able to breathe now. Okay, so I want you to be able to breathe. So we can't do these experiments, nor do I have the equipment to evacuate all the air and let things experience true free fall. But we can approximate it. And anything here on Earth, we have learned, scientists have learned that things accelerate down to the ground at about 10 meters per second per second. So the free fall acceleration here on Earth, near the surface of Earth, is about 10 meters per second per second. To be more precise, it's about 9.81 meters per second per second. But notice that if I round 9.81 to 1 sig fig, it's 10. So very often what we'll do, especially with a multiple choice question, is we just round it to 10. It makes the math a lot easier, because most of us can multiply or divide by 10 in our head, and therefore we don't necessarily even need a calculator. We can just look very quick at what the best answer would be. All right, wait for everybody. All right, can I go on? All right, we're now going to do a thought experiment, because again, I can't do this in real life. So I want you to imagine that we have a hammer and a feather. Can you imagine that? One hand I have a hammer, the next one's a feather. And I'm going to drop them from the same height at the same time. So imagine this is my feather, this is my hammer, and I'm just going to let them go from the same height at the same time here. Can you envision that? Just they're not these objects. This is a hammer, this is a feather. Okay. Now, suppose that air resistance can be eliminated. This is where me doing it, I can't do it in front of the room right now. Can't, because I can't get rid of the air resistance. But imagine I could. Neither of the hammer nor the feather experiences any air drag or air resistance as they fall. I want to know which one hits the ground first. Now, I don't want you answering it. I want you to write it down in your notes. I want you to make a hypothesis. Take a guess. What do you predict will happen? What do you think will happen? Will the hammer hit first? Will the feather hit first? There's actually two other answers. Neither one gets to the ground when I release them. Or do they both get to the ground at the same time? What do you think? Those are the four answers. Hammer gets there first. Feather gets there first. They don't get to the ground at all when I let them go. Or they both get there at the same time. What do you think? You have a guess? Something written down? Okay, your grade doesn't depend on this. What we're going to now see is what happens. You can write next to that, hypothesis. Hammer feather experiment, hypothesis. Now, we actually have done this experiment before. When I say we, I don't mean you and I mean humankind, we. And it was done back during the Apollo era missions, which happened in the late 1960s, early 1970s, trying to get to the moon. These missions were all about leaving Earth's orbit, leaving the Earth, going to the moon. Apollo 15, we first got to the moon in Apollo 11 was the mission where we actually landed on the moon the first time. You may have seen a movie, Apollo 13, which was about the 13th mission in the series. And that's the one where anything that could go wrong did, but somehow they were able to get back to Earth. Everyone survived it. Spoiler alert. Sorry if you haven't seen the movie. Watch it. It's all factual. Really good. Tom Hanks is in it. Kevin Bacon's in it. All these big time actors. It's a phenomenal movie. If you haven't seen it, maybe I'll get to show it to you someday. Maybe we'll do that someday just for fun. Anyway, can't do it now. But anyway, here we go. Here's that experiment from the Apollo 15 mission.
Well, in my left hand, I have a feather. In my right hand, a hammer. I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects and gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. And the feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
All right, so we can see that on the moon, they both landed at the same time. How many of you predicted that would happen? Okay, so a lot of you remember that from middle school. I think they hit that home in middle school. But here we are talking about it again. Can you tell me why? Why did they both hit the ground at the same time there? Any ideas why? Brayden? Yeah, they have the same acceleration downwards. That's right. That comes from the moon or the planet that you happen to be on. So let's talk about some differences between the Earth and the moon that prevent that from being true right now here in our classroom. If I were to do that with a hammer and a feather, which one would get to the ground first? The hammer. I mean, you can see that with this textbook and this piece of paper. If I do that, obviously the textbook gets there faster, not the paper. You see the paper floating. Just look at the falling leaves off the trees right now. You'll see the leaves go, oh, this. Why do you think they're doing that? Because air is pushing back up. Here on Earth, we have a very thick atmosphere. What does it mean to say we have a thick atmosphere around the Earth? It means that the molecules that make up the air around the Earth are very large molecules. O2. That's 2 oxygen molecules bound together. Those are big. Nitrogen, N2. Those are big molecules bound together. Carbon dioxide, again, CO2. C with 2 oxygens attached. It is a big molecule. Those big molecules cause objects that fall through the air to experience large air resistance forces. Basically, think of it this way. As the object falls through the air, it hits all those big things. Those big things slow it down as it goes downward. And that's why the paper, as we just saw, doesn't get there first. On the moon, however, what's different is that the atmosphere around the moon is very thin. There is air. It's just not the same kind of air that we have here on Earth. The molecules that make up the air on the moon are much smaller, which makes it much easier to move through them on the moon. And so effectively, that allows us to reproduce experiments on the moon that have 0 air resistance, effectively 0 air resistance, because the air there is too thin. Now, interestingly, you know, the astronauts in space and on the moon, you saw the astronaut there on the moon. He's wearing a spacesuit, very similar to this. This one has a jetpack attached to him, so he can speed himself through space, okay? But the one there didn't have the jetpack. But the suit is there for 3 reasons. Number 1, so that way they can breathe oxygen-rich air. We don't have that on the moon. So they have an oxygen tank attached, so they're breathing in oxygen-rich air. Number 2, there's a lot of solar radiation on the moon that isn't reaching us here on Earth because our atmosphere has an ozone layer, which prevents all of these cosmic particles from reaching you. Basically, if you didn't have that spacesuit, but you still just had an oxygen tank attached to you, you would get a really, really, really bad sunburn like that on the moon. Because all of that solar radiation would be reaching you without any layer of protection between your skin and those particles. So that's another reason we have a spacesuit. The third reason is because that atmosphere around the moon doesn't insulate the moon, doesn't keep heat in like our atmosphere keeps heat in to the Earth. So therefore, if you're on the moon and you don't have that spacesuit, you're going to get frostbite like that. Okay? It's really cold. So it's important. That's why that we have spacesuits like that. So therefore, because of the thin atmosphere and no air resistance, we get rid of that atmosphere and we see that the 2 objects hit the ground at the same time. It has to do with the difference in the air molecules that we're moving through. Now, interestingly, I said I can't do this here on Earth. That's true. But I can try to replicate it. Okay, so I'm going to do it with this textbook and this piece of paper again. I'm not going to drop them the way I did before. You all saw that, right? You saw the textbook hit before the paper. The way I can get the paper to hit the ground or my desk at the same time as the book is to do this. Did I change the mass of the paper at all by crumpling it up? Okay, so watch what I just did. You watching? Which one hit first? You want me to do it again?
Yeah. Even Stevens.
Yeah, they fell together. Did you see that? They were falling together. Why did crumpling the paper change that? Because I reduced the surface area of the paper that's in contact with the air. So by reducing surface area, we can see the same kind of experiment here. Now, they mentioned in the video a scientist named Galileo Galilei. Let's talk a little bit about him. That's the fellow up there on the top left. That's his portrait. He lived from 1564 to 1642. Some of you may be familiar with him because of Bohemian Rhapsody. They mention him in the song Galileo, Galileo, Galileo Figaro. You know what I'm talking about, right? You know that song? Okay, so there we go. So Galileo is the scientist responsible for this. He did some experiments located here. What is this? Okay, you all know the Leaning Tower of Pisa. Anybody ever been there? Okay, Miss Creasy went this summer. I saw some pictures on Facebook of her and her family at the Leaning Tower this summer. I went there in summer after my junior year of high school with my family. Got lots of families still in Italy. So we were there for a month, not in Pisa, but all of Italy. And one of the towns we stopped in to see things. We went to Rome to see the Colosseum. We went to Venice to see the gondolas and the canals. And we went to Pisa to see the Leaning Tower. The tower is not as impressive as it looks. It's about as tall as our towers of Colonnade. Towers of Colonnade, nobody's coming to visit those from across the globe, right? The only reason this tower is so famous is because it leans and hasn't fallen over. They are trying to keep it in that position. They don't want it to fall all the way over because then nobody's going to go there. They don't want to erect it and stabilize it in a vertical position because then nobody's going to go there. They were trying to make money off of people. There's only 3 things in this town. This tower, behind it is a church. Woohoo! There's a church in every corner, on every corner in Italy. And then behind it is a cloister, which is like a monastery where the nuns live in silence. That's it. Since 1585, when Galileo did his experiment, all these little, well, nowadays, there's all these like little pizza shops and gift shops. Why are those things creeping up? Because they're trying to make money off of the tourists who are there. Italians are kind of resourceful that way. They're trying to make money. I could say that. I'm an Italian. We are resourceful. We try to make money off of people if we can. So it's not really that big. The doorway to the Leaning Tower is really small. It's about half the width of this door. About half that width, about 15 stories tall, maybe 10 to 15 stories. And according to legend, Galileo went up to the top of the tower with 2 different cannonballs, and he dropped them at the same time off the tower. Apparently, he did this in 1585. And according to the legend, one of the cannonballs was 10 times more massive than the other. Now, you see, I'm saying legend. The legend, I don't think is true. I don't think Galileo did this. I think what he did is what like a lot of college professors will do with their graduate students. They take credit for the work, but the graduate student didn't. They just watched what happened. I think that's what Galileo did. And let me explain why. If you ever research Galileo, you read about him, you will learn 2 things, which I think makes it impossible for him to have done this. Number 1, bless you, Galileo was a really large guy. Okay. Well, how big did I say the door is? About half the width of ours. Okay. Half the width. The stairs are that width. Okay. It was like this. Okay. Secondly, he was really ill most of his life. Is a really large, ill man going to carry 2 cannonballs? Think of them like bowling balls. One bowling ball, the other one's 10 times heavier, up 15 flights of stairs. What do you think? I think you're coming to the same conclusion I am. There's no way he did it. But he was also wealthy. So guess what he probably did?
Maybe.
He probably gave a poor, this is Renaissance, serfs. Probably paid some poor peasant with a loaf of bread and said, here, go on up. And did it. Maybe 2 of them went up. 2 loaves of bread. There you go. And he just watched what happened. I'm guessing that's my theory. I have no proof of that because I wasn't alive in 1585. I know I'm old, but I'm not that old. Anyway, he noticed he wrote about these two cannonballs landing at exactly the same time. Now, why did he probably realize that? Because both cannonballs were the same size. They had the same shape. One was just heavier than the other. So the surface area, the air resistance factor was exactly the same for both. Okay. We're just going to talk one more slide about air resistance and we're done. From that point forward, we will never talk about air resistance again, and we're going to pretend it doesn't exist. So what he proved, this experiment he did, proved that all objects, right here, all objects fall with the same acceleration regardless of their mass, okay, or their density. And this value that he came up with for this acceleration for objects falling on Earth is given a special symbol. It's a lowercase g, which we'll talk about in a minute on your reference table. All right. Okay, let me try to get through the rest of this fairly quick. So that's the experiment that proved that all objects fall at the same rate. They all fall at the same rate regardless of their mass. So this last piece about air resistance, as I mentioned, I don't know that you have to write this down, but where does it come from? As I've said, it comes from the collisions between an object's surface and the air molecules. So there's really two things which affect how much air resistance you experience. We talked about the cross-sectional area. That's the surface area. We didn't mention the speed. Here's how speed does affect how much air resistance you experience. The faster you go, the more air resistance you feel. Let me give you an experiment you can do later. When you're driving in your car, whether you're driving or you're a passenger, just open the window. Stick your hand out the window. Okay, go really slow, like 1 to 2 miles an hour. What are you going to feel in your hand? Not much. Now go at 15 to 20 miles an hour. What are you going to feel? You're going to feel your hand get pushed back a little bit. What's pushing your hand back? The air. That's air resistance. The faster you go, the more air you're moving through, the more air resistance you experience. Okay, so those are the two most common things. There's a little animation showing here on Earth. If I dropped an elephant and a penny, the elephant gets there first. We're not doing that in real life. Sorry, I don't have an elephant to drop off the roof, nor am I going up on the roof to drop anything off. All right, so as I mentioned a minute ago, we have a special numerical value for the acceleration of objects in free fall. This is called the acceleration due to gravity. It's the rate at which our velocity will change when we fall. As I mentioned, we have a special symbol to denote this. It is a lowercase g. Now, what I'd like you to do is turn to page 6 of your reference table. And on page 6 of your reference table, in the right-hand column, you will see that little g right here. Go ahead and check that off. You see what it defines it as? The acceleration due to gravity. Since it's an acceleration, it's a vector. It will be a vector. So I'm putting my little arrow over the top of that to remind me that it is a vector. Acceleration due to gravity. It's also called the gravitational field strength, but we're not going to refer to it that way yet. Now, on the Earth, the value that we use, it's planet dependent, is 9.81 meters per second directed downward. You see, I'm giving you a direction there. That tells you it's a vector. That's the value that we use here on Earth. And this is a special value which is given to you on page 1 of your reference table. So if you could please turn to page 1, you'll see here on page 1, it defines that little g for us. There's our acceleration of gravity. This is its magnitude. Do you remember what its direction is? Down. Yeah, so I'm just going to write down. Because it's down, usually down is the negative direction. So when I use it in a problem, I'll make it negative 9.81 meters per second squared. And I want to check that off. That's our first constant to check off in that list of physical constants. Now, to be honest about this, that 9.81 is just a number that New York State has said this is what we're going to use for your regents. We do see slight variations in this number based on your altitude around the Earth, meaning how high or low, above or below sea level you are. Here in Albany, we're just a little bit above sea level. So our value is pretty close to that 9.81. If you were to go to Denver, Colorado, though, Denver, Colorado, I think is 2,000 feet above sea level. That's not the value there. It's about 9.78, I think is what it is. If you were to go to New Orleans, Louisiana, that's below sea level. It's probably like 9.82. So we do see small variations in this based upon our altitude. It's all based on our distance away from the center of the Earth. And so what you'll see us do, if we want to make some approximations to do multiple choice questions faster, you might want to approximate that value to 10 meters per second squared instead of 9.81. Just makes the math a little bit easier to do in your head. But if you're going to do something precise, like a show work question on a test or quiz, or if you're doing a lab, you absolutely cannot approximate. You have to use 9.81. Okay, so now what we're going to do, now that we've defined this acceleration due to gravity, we're going to talk about everything we did in Unit 3 in like 10 minutes about gravity and accelerations from gravity when objects fall, which means we're going to start off with the vocab. This is the concept of what acceleration due to gravity is and where it comes from, but let's now deal with the vocabulary of this. So, and our motion diagram. So that's a ticker tape of an object that's dropped. So you might want to sketch that in real quick. You'll see that there's 6 dots. This is time 0 seconds, 1, 2, 3, 4, and 5 seconds. Notice that the dots are getting further and further apart as it falls. So your ticker tape here would be read with an arrow going down. You would be looking at that going down. Notice that on that ticker tape diagram, we are seeing that the distance we travel every second in the downward direction is getting bigger and bigger and bigger. What does that mean? It means that we are speeding up as we fall down to the ground. And since the downward direction is the negative direction, we're speeding up as we go down. It means our acceleration is also down, same direction. Okay. So that's our ticker tape, our motion diagram, describing what we see on that ticker tape. May I go on? Anyone need me to wait? Jenny, you can also get these off the slides posted in Google Classroom for the unit. Okay, so remember that when we have any kind of acceleration, we're talking about how quickly our velocity changes. How much is our velocity changing every second? So if I have an acceleration that's about 10 meters per second, that means my velocity is changing by 10 meters per second every second. So what's really interesting about when I drop something, do you know what velocity it's going to start from when I drop it? Yeah. So this is a data table showing me the velocity of a dropped object over the 5 seconds. So notice at time 0, that's our initial velocity. We're going to start from rest, a velocity of 0 meters per second. After 1 second, my speed is about 10 meters per second. At 2 seconds, it's about 20 meters per second. After 3 seconds, it's about 30. Notice we're seeing a change of -10. The negative means down. So on my ticker tape, if I were to label the speeds at every time, I would start with 0, then I would be 10, then 20, then 30, then 40, then 50. Guess what the next one would be? 60 meters per second. It would change by about 10 meters per second every second. Sorry, I'm dying. I know it's not hot in here. A little bit? Okay, good. That makes me feel a little better. If it were up to me, I'd be getting air conditioning in here and it would be like 65 in here, if not cooler. And so that way I felt comfortable, but I could just fan myself.
You should get like a neck fan.
Not a neck one. Didn't I have this out earlier this year? I have a fan. I could just.
There.
Good idea. I am. It's uncomfortable. I just can't walk around or I'll trip myself. Here we go. I just gotta stay right there. Okay. Good idea. Forgot. I have my little portable fan. That was from, was it last year? Last school year, the first day of school, the classroom got to like 100 degrees. Remember that? So I went out that night and bought all these little fans. My students were looking at me. I'm like, oh, and they're boiling. I'm like, sorry, go get your own fan. Okay, let's talk about our graphs. The position time graph needs to be a parabola. Why does it need to be a parabola? Because that's what shows us an object is accelerating. That is a sketch of the position time graph for an object that gets dropped. Now let's talk about what we see. The y-intercept there. If I were to read a number right there at the y-intercept, that would tell me what height I was dropping it from. I can read that off the graph, the height at which I'm dropping it from. A 0 meter position right here is the ground. That's where the ground is. So I can read the height that it's being dropped from the graph. Now what I see here is a parabola that shows an increasing speed, a speeding up motion as it goes down. Remember that generally slope is velocity, and this graph starts off pretty horizontal. That is a 0 slope. If I were to draw a tangent line there, it would start off horizontal tangent line. So that means the initial velocity is 0 meters per second. It ends up pretty steep, which means that I'm going really fast when I get to the ground. And it's negative, which means I'm going down toward the ground. Okay, can I go on? All right, let's talk about the velocity time graph. Notice this graph is exclusively down in the negative quadrant. And it's a diagonal line. Remember, we expect diagonal lines on velocity time graphs because that's what shows the acceleration. When I read off from the graph, my initial coordinate at time 0 is 0 meters per second. That's my initial velocity. I have to start off at the origin for something that's dropped because that's a 0 meter per second velocity. Notice that when I end the graph here, I end up with a pretty big negative number. The big number tells me I have a large final velocity. I was going fast when I got to the ground. And notice they're all negative down in the fourth quadrant, which means the entire time I'm heading down to the ground. Right? And I'm speeding up as I'm moving down to the ground. Also remember that the slope on this graph is your acceleration. So notice that we have a negative slope that doesn't change throughout the entire line. So what that means is we have a constant negative acceleration. And that acceleration is about negative 10 meters per second here on Earth. Okay, so that takes care of, yes, Ashley. Okay, that's after it's hit the ground. So have you ever dropped something like in sand or loose dirt? What do you see after you've dropped it in there? You take it out. You see it like a crater, a little bit of a crater. That means it was moving down when it hit the ground. So when we talk about that final velocity, it's the velocity before the impact at the ground. What you're thinking of is the velocity after the impact.
What happens if it bounces?
Okay, we're not going to talk about that now. That will come in unit 8.
Oh, now
We got a ways. We got a little ways to get there. But you're thinking ahead. Okay. Now, the last thing we need to be able to do with these objects which just fall, and assume they're going to fall forever, okay? I need to be able to ask you to calculate things like how far did they fall? How fast were they moving when they got to the ground? Not after impact, but before. So we need to use our guess method to do this. And when we do our guess method, there are 2 givens that will never be explicitly stated in a question. The first thing we expect that you know is if that we are doing this on the Earth and you are dropping it, the word dropped indicates the initial velocity is 0 meters per second. You're always going to drop something from rest. You are not chucking it down to the ground. You're not heaving it down. You're just letting it go. Just let it go. Start from rest. And since the next thing we know is that we are on Earth, we will know the acceleration. That acceleration is that special value that we just checked off on page 1 of our reference table. The acceleration of gravity here on Earth, 9.81 meter per second squared downward. More useful if we write it as just negative 9.81 meter per second squared for a guess method problem. Okay. So those things won't be told to you. You just have to know that you got to use those to help you solve a question. Keywords to help you with that. Dropped, Earth. You can't use this number if you're on the moon. The value on the moon is about 1.67 meter per second squared. Mars is about 3.89 meter per second squared. Okay. Questions? That's the end of the presentation. So that's where I'm going to stop. We have 3 minutes left. I was